Good afternoon, everyone. My course title is Engineering Physics. The topic is Molecular Crystals. I'm G. Rakshita from CSC AML Section C. Now enter into the topic. What are molecular crystals? Molecular crystals are solid substances where the lattice points are occupied by discrete molecules rather than icons or atoms, held together by weak intermolecular forces. Constituent particles maintain their individual identity. Examples include dry ice, CO2, iodine, I2, and sucrose. Intermolecular forces. The stability of molecular crystals depends on non-covalent interactions, which are significantly weaker than ionic or covalent bonds. London dispersion forces, present in all, dominant in non-polar molecules. Dipole-dipole interactions occur between polar molecules. Hydrogen bonding, strong directional forces. Example in ice and in DNA. Optoelectronic materials, design of molecular crystals for organic semiconductors like LEDs and nonlinear optical devices. Advanced functional materials, exploration of crystals with tunable magnetic, electrical, or thermal properties for non-technology applications. Computational design, use of AI and molecular modeling to predict and engineering crystal structures with desired properties. Sustainable synthesis, development of environmentally friendly and cost effective crystallization methods. General physical properties, low melting points, weak intermolecular forces requires little energy to break, leading to low melting and boiling points. Soft and volatile. Generally soft in textile, many sublime like dry ice or wave high vapor pressure. Electrical insulators. Electrons are localized within molecules, preventing electrical conductivity in the solid state. Classifications of molecular solids: non-polar solids and polar and H-bonded solids. Non-polar solids are composed of atoms, noble gases, or non-polar molecules like H2, Cl2, I2, held by weak dispersion forces, soft, low melting points, and non-conductors. Polar, held by dipole-dipole forces, example SO2, higher MPs than nonpolar. H bonded. H bonded to FON, example ice. Strongest among molecular solids. Case study of ice is known as H2O. Ice is the quite, quintessential hydrogen bonded molecule crystal. Each oxygen atom is tetrahedrally coordinated to 4 hydrogens. Open case like structure results in lower density than liquid water. High enthalpy of fusion relative to molecular mass due to extensive H bonding network. That dry ice, CO2, nonpolar molecular crystal. Carbon dioxide crystallizes as a face-centered cubic structure, held together by weak London dispersion forces. Sublimation transitions directly from solid to gas at 78.5 degrees Celsius at 1 atmosphere. Used widely for refrigeration and as a precursor in chemical synthesis. Iodine I2. Iodine forms dark violet lustrous crystals that demonstrate typically nonpolar molecular solid behavior. Diatomic I2. Molecules arranged in layers. Weak van der Waals forces between molecules allow them to slide, making the crystal soft. Readily sublimates into a violet gas up to general heating. Polymerism. Same molecule, different structures. Polymerism is the ability of a solid materials to exist in more than one crystal structure. Different packing arrangements led to different physical properties: solubility, melting point, density. Crucial in pharmaceuticals where different polymers have different bioavailability. Pharmaceutical applications: development of novel drug formulations with improved solubility, stability, and controlled release. Polymorphism case study: Ritonavir. The challenge: Ritonavir, an antiretroviral drug, originally existed as Form I, suddenly a more stable, less soluble Form 2 appeared during manufacturing, causing the drug to precipitate out of solution and fail dissolution test. The solution is that the product had to be recalled and reformulated. The highlighted the critical importance of identifying and controlling stable molecular crystal polymers during drug development. Crystal engineering: the design and synthesis of solid state structures with desired properties. Supramolecular synthons. Using predictable non-covalent interactions like H-bond motifs to assemble molecules into specific architectures. Co-crystals: crystallizing an active formaldehyd ingredient API with a conformer to improve solubility without changing the chemistry. Crystal growth methods. Solution growth: slow evaporation or cooling of a saturated solution, common for organic molecules. Melt growth: controlled cooling of a liquid melt. Example: zone refining. Vapor transport: sublimation and redeposition used for high purity organic semiconductors like pentacene. X-ray diffraction: the fingerprint of crystals. Powder X-ray diffraction (PXRD) is the primary tool for identifying molecular crystals. Constructive interferences of X-rays by crystal planes obeys Bragg's law. N lambda equals to 2d sin theta. Used to distinguish polymers and determine crystallinity. Thermal analysis (DSC) is nothing but differential scanning calorimetry. Measures heat flow associated with phase transitions, essential for determining melting points, glass transitions, and polymorphic transformations. TGA, thermogravimetric analysis, measures mass change with temperature, used to detect solvates, solvent loss, and decomposition temperatures of molecular crystals. Application: pharmaceuticals. The vast majority of drugs are formulated as molecular crystals. Solubility of bioavailability directly linked to the crystal lattice energy. Stability: the chosen crystal form must be stable over shelf life, avoiding hydration or polymorphic shifts. Processing: crystal habits, shape, affects flow, and tableting properties. Organic electronics. Organic semiconductors. Molecule crystals like pentacene and rubrine are used in OFETs is organic feed effect transistors. OLEDs. Organic light emitting diodes. Organic photovoltaics. OPVs. Transport occurs via pi stacking overlap between molecules in the crystal lattice. 2D molecular crystals. Recent research focuses on growing 2D molecular crystals monolayer thickness for next generation Electronics. High mobility. Reduced disorder compared to thin films. Flexibility electronics. Mechanical flexibility suited for wearable devices. Sensors. High surface to volume ratio makes them excellent chemical sensors. Current challenges. Prediction. Predicting the exact crystal structures solidly from molecular diagram CSP remains computationally expensive and difficult due to weak forces. Purity. Impurities can drastically alter crystal growth habits and electronic properties, especially in organic semiconductors. Preventing unwanted polymorphic transitions during storage and usage of is a constant battle in industry. Thank you.